Okay, so we're going to look at compound interest. And we have two formulas. And if we're compounding periodically, like say for part A twice a year, which is semi-annual, or quarterly 4 times a year, n equals 4, or monthly, which would be n equals 12, then we're going to use this formula over here. Now, continuous compounding is going to be from this formula over here. And essentially, if we let n get infinitely large, say going from compounding quarterly to monthly, and go from monthly to daily and daily to hourly, and just keep making this value of n larger and larger, so we're compounding more and more times a year, we're actually, this function here is getting closer and closer to this function. So in calculus, we have a thing, if we say we let n go to infinity, then these two expressions become equal. So that's kind of the idea. It's a useful trick. It's great when you want to go from working with a discrete system to a continuous system. So you can use a lot of stuff from calculus that way. It makes things nicer. But anyway, that's kind of the difference between the two formulas. And the reason we have a 1 here is because if you can think about it, if you get rid of the nt, p times n over r would give you the earned interest, and p times 1 is the initial investment. So that essentially says the value after one period is the initial investment plus the interest earned on the investment. And if we keep repeating this formula over and over again, that's where we get the nt from. And that's kind of the gist of it. And if you let n go to infinity, then you get the continuous compound case. But anyway, let's look at the problem. So for this problem, parts A, B, and C, we have a finite n. N is 2, n is 4, is n 12. So we're going to use this first formula. And the interest rate is kind of like your APR, is given by 0.06. The initial investment is going to be 10,000, and the number of years, which is t, is always going to be 5. N is the number of compounding periods per year. So for part A, n equals 2. So let's just set this up since it's going to be the same for all the problems. A is going to be equal to 10,000. This is for part A. Times 1 plus 0.06 divided by 2, or n if you like, raised to the n times 5. Now for part A, we're going to have A is equal to, now this is for part A, n equals 2, is going to be equal to 10,000 times 1 plus 0.06 divided by 2 raised to the 5 times 2 is 10. Because n is going to be 2 for this case, and 5 times 2 is 10. So we wind up with this. So now how can we calculate this? Well, 0.06 divided by 2, if you did in your calculator, is 0.03. So this is going to become A is equal to 10,000 times 0.03 plus 1. If you're doing PEMDAS, remember you do you start inside the parentheses, so we're going to do inside the parentheses first. 0.06 divided, then the next inside the parentheses you have addition and division. Well, working inside the parentheses here, all we have is division and addition. And division outweighs addition, so we're going to do the division first. And this is going to become 1 plus 0.03 raised to the 10. Now, working inside the parentheses, all we have left is addition. So this is going to become A is equal to 10,000 times 1.03 raised to the 10. Alright? Now, at this point, I probably just want to do it in my calculator, because what I'm doing is I'm multiplying 1.03 times 1.03 times 1.03. So what I'm going to do is I have two operations going now. I have multiplication, which I have 10,000 times all of this, and I have exponents, 1.03 raised to the 10. Well, exponents come before multiplication using PEMDAS, so I'm going to take 1.03 to the 10, and I'm going to multiply by 10,000. Okay? And I am going to do that as soon as I can get the cap on my marker, because it's stuck. I guess that's not your problem. Oh, there I go. Okay, so what I'm going to do is I'm going to pull up Excel. And what can we do here? We're going to I'm going to just use it like your calculator. It's going to be 1.03 raised to that little arrow that you can usually find on Shift 6 on a keyboard. And I'm going to raise it to the 10th power. So that means 1.03 raised to the 10. And now I want to multiply that number 10,000. So if in your calculator, you just hit multiply, type in 10,000 equals. I'm going to type in equals, hit this number over here, and say times 10,000. Okay? So what we're going to have here is, this is going to be equal to, 10,000 times 1.343916, which is roughly equal to 13439.16. So $13,439.60 approximately. So let's go back to the other screen. Here we go. So again, to do the steps, we just plugged in n equals 2 to our formula, and 5 times 2 is 10, so this is going to become 10. The next step is 0.06 divided by 2 gives us 0.03. Working inside the parentheses, we did the division first because we're starting always first in the parentheses, whatever those are. Then 0.0, then inside the parentheses we have division and addition. Well, division outweighs addition, so we can do 0.06 divided by 2 gives us 0.03. Still saying inside the parentheses, 1 plus 0.03 gives us 1.03. Now what we have is 1.03 raised to the 10, which is exponents, and I can get rid of the parentheses if I wanted. They're just there for organization at this point. Because I have 1.03 raised to the 10 times 10,000. Well, exponents come before multiplication, so 1.03 to the 10 is 1.343916. And of course, I multiply that by 10,000, and I get $13,439.16. Okay, and that's part A. Now I can repeat the parts. I can repeat this for parts B and C, and D is going to use the other formula. But let's see how I can do this in Excel just to speed things up. It's the same procedure for the other parts you can do in your calculator. But what I'm going to do is I'm going to use a spreadsheet. So a spreadsheet's really popular, and if you want to do it on the calculator for the other parts, it's exactly the way I did it. and you can check your answers from what I'm about to do. And I'm just going to hard code. I'm going to type R, P, and T. And for R is going to be 0.06, which is 6%, or 6 divided by 100 is 0.06, and that's what 6% means. P is the initial investment, is going to be 10,000. T is going to be 5. So those are those values. Now I'm going to type N over here. And N is going to be 2, 4, and 12. Now I'm going to put my formula for A. I'm going to hit the equal sign because it's going to be a formula. And it's going to be P. So B2 is because when I selected the value for P, it just means it's column B, row 2. And I'm going to put dollar signs on it. And dollar signs means that it's going to treat it like a constant, and the computer is not going to change or do anything to this value. So it's going to be the initial value times, open parentheses, 1 plus R, which is 0.06. It's going to be this value here. Now this is going to be the same for all the problems, so I'm going to put dollar signs around B and around 1 also. Divided by N. Well, N is over here, and that's case A. Now, for this one, I'm not going to use dollar signs because N is going to change for the different parts. So I'm just going to do that. And I'm going to close parentheses, and I'm going to raise. Now I'm going to have two things here. So I'm going to open parentheses, and it's going to be N again times T, because in each case it's 5 years. And that doesn't change for any of the problems, so I'm going to put those in parentheses. Now if you don't want to do it this way, it looks confusing, you can do them all like I did part A, and you can just check your answers like I did for the other ones. Okay, so I should get $13,439.16. Now what I'm going to do is I'm going to select it. And you see how it's a white cross? Well, if I drag it to this corner over here with the knob, it's going to turn into a black cross. And I'm going to left click, and I'm going to drag down. Now, the only thing that's not going to change in any of these is the only thing that's going to change is going to be my N, because everything else is a fixed value. So the dollar signs means that when I drag it down, it doesn't change the value. It doesn't change these values. The only thing that changes is the N. And when I dragged it down, it just used this N for the first one, this N for the second one, and this N for the third one. So I wind up the values are 13,469 for the first one. 13,468 for the second one, and $13,488.50 for the third one. So 12 compounding 12 times per year is the best, according to these. Now we're going to go on, and we're going to do the continuous compounding. Now for the continuous compounding, we're going to use the formula A is equal to P times e to the RT. And to get this formula, you have to use calculus, and what you do is you let n go to infinity, and as n gets bigger and bigger and bigger and bigger and bigger, it's getting that formula for compound interest where you have the discrete time steps where you have you're compounding semi-annually, monthly, quarterly, daily, and keep going. As you let n get bigger and bigger and bigger, that formula for A gets closer and closer to this formula. So if you say you let n go to infinity, what this means is you're compounding all the time. This is the formula you wind up with. So let's see how this works. So r in the problem is equal to 0.06, and p is equal to 10,000, and t is equal to 5. Now there's no n in here. Essentially n is equal to infinity or something like that, right? However you want to think of it. So we don't have to do anything with n. It's already built into the problem. So a is equal to 10,000 times e to the 0.06 times 5. So we have to use a calculator for this, and we're going to start out by taking 6 times 5 is 30, and we're going to move 2 decimal places over, so 0.06 times 5 is just 0.3. So we're going to have a is equal to 10,000 times e to the 0.3. Now this is an exponent, so what we're going to have to do now is we're going to have to do e to the 0.3, and e is a number. It's kind of like pi. You can't really write it down, so you put in your calculator and you get a bunch of decimal places. So if we do it in our calculator here, I'll do it in Excel. And to do it in Excel, you do exp and type the number you want to raise it to. If I want to just the number e, I would do a 1, and that's approximately what e is. But we want to raise exp, or we want to raise e, and in Excel you do equals exp to the 0.3, and then we want to take that number e to the 0.3 and multiply that by 10,000. Now, notice I'm not using dollar signs here. The reason I use dollar signs for this is I wanted to drag it down, and I wanted to keep these things constant, but change for these. If I'm not dragging anything, I don't have to use dollar signs or worry about it. So that gives us a value of 13,498. So that's $13,498.59. And as you can see, and I'll go through the order of operations on the paper in a second. You can see this is the value for continuous compounding. This is monthly, quarterly, and semi-annually. You can see the best thing you can do is compound all the time, but you can see it doesn't give us a huge improvement. That's because as we compound more often, the rate of increase that we're getting money is going up, but the rate that it's going up is slowing down. So it's not getting bigger by leaps and bounds, but it is going up. So the best thing you can do is compound continuously, and continuous compounding is very useful in mathematics for financial modeling if you get into like the real sophisticated stuff. Not really something you would ever use on your own portfolio, but if you work for like a big company and you're trying to model certain processes or things like that, you would definitely come up. So again, we have a equals to 10,000 times e to the interest rate times 5. Well, we want to do exponents first. Well, the exponent has multiplication, and so we have to multiply these together to get 0.3. And then we have multiplication and exponents. We do exponents first. So we do e to the 0.3. So it's going to be 10,000 times 1.349859. We multiply that by 10,000 left. That's the only thing left to do. We have $13,498.59. And that's our continuous rate. Now, we had another question. And the next question that was being asked was concerning, let me go to, a person had a question with long division. So let's see. I'm going to go over that. And the question is, we want to use polynomial division to divide x plus 9 into x squared plus 6x plus 11. So we have over here, and the basic idea is, you're going to move to the paper in a second, we have x squared plus 6x plus 11 divided by x plus 9. Or, okay, so let me do Alt Tab and go over to the document camera. So I'm going to write it three different ways. X squared plus 6x plus 11 divided by x plus 9. So there's three ways to write it. And in order to do the problem, we're going to have to write it like this. Unless you're clever, you can play around and get this to work too. But it's not like a straightforward method. It's just kind of trying to, well, I won't bother with that. So the problem can be written by x squared plus 6x plus 11 divided by x plus 9. Or it can be written by, which is the same as x squared plus 6x 11 divided by or over x plus 9. Or we can write it this way, which means x squared plus 6x plus 11 divided by x plus 9. Or when they write it this way, sometimes people say x plus 9 into x squared plus 6x plus 11. Now notice that I have in both the divisor and the dividend are written in terms of increasing order of x powers. So here the x squared term is first, then the x1 term or x to the 1 is here, and the x0 or x raised to the 0 term or the constant term goes last. And again, the x term of highest order here is just x to the 1, which is x, and this is an x0 term, just a constant, goes last. So once we have this, we start with the x term, and we say how many times does x go into x squared? It goes x times, and we say x times x is x squared. Now, we're always going to flip the sign because we want to subtract. So x times x is x squared, and the reason x goes into x times is because x times x is x squared. We're asking what time x times what gives me x squared, where x times x gives me x squared. So x goes into x squared x times x is x squared, but when we bring it down, we flip the sign because we're subtracting. I don't want to go why into flipping the sign is equivalent to subtracting the polynomials, but we're always going to flip the sign before we bring it down. Then we're going to do x times 9 is 9x, but we're subtracting, so we flip the sign, we're going to make it minus 9x. And if you want, you can put a plus 0 over here if you like, since there's nothing there. Now, x squared minus x squared is 0. 6x and negative 9x is negative 3x. And 11 plus 0 is just 11. Now you can forget the 0 if you like, it doesn't matter. And we're going to start over again. We're going to do x goes into negative 3x, negative 3 times. Why? Because We're asking x times what is negative 3x? Well, x times negative 3 is negative 3x. So we put a negative 3 over here, because x goes into negative 3x negative 3 times. And we have negative 3 times x is negative 3x. But we flip the sign because we're subtracting, so we're not going to put negative 3x, we're going to put positive 3x. Again, x times negative 3 is negative 3x, but we're going to subtract. So we flip the sign to make it positive 3x before I bring it down. And then we have negative 3 times 9 is negative 27, but we're subtracting, so we flip the sign before we bring it down. So it's going to be positive 27. And the 3x's cancel out to give me 0. And I can forget the 0 if I want. And 27 plus 11 is 38. Now, I have x does not go into 38 at all. I have a variable and a number. I can't do that. So that tells me I have a remainder of 38. So now what I can do is I can write my original problem, which is x squared plus 6x plus 11 all over x plus 9, which is the original problem, is going to be equal to my quotient, which is the number over here, which is going to be x minus 3, plus the remainder, which is 38, divided by my divisor, which is x plus 9. So it's the same thing as long division with numbers. You can write it as a quotient plus the remainder over the divisor. An example, say with numbers, if I did 5 into 21, or let's say 5 into 73. Well, 5 goes into 7 one time. 5 times 1 is 5, but I flip the sign because I'm subtracting. So it's going to be minus 5. And if I want, I could put a 0 there, it doesn't matter. And 7 minus 5 is 2. And I can bring down the 3, or I can put a 0 there, and 0 plus 3 is 3. And I start over again. 5 goes into 5 goes into 23. Well, 5 times. And 4 times. 5 times 4 is 20. But I'm subtracting, so I'm going to flip the sign, so I'm going to do minus 20. And I subtract 3. Now, 5 cannot go into 3. So what I can do is I can write my original problem as 73 divided by 5 is equal to my quotient, which is 14, plus my remainder over my divisor, which is 5. So 73 over 5 is going to be 14 3/5. And you can check that by combining the fractions, and doing 14 times 5 is going to be 70 plus 3 is 73. So if you simplify the fractions again, you can check and get 73 over 5. Okay? So I hope that answers all the questions that people had. Sorry for the delay on the video. And I hope to hear again from you soon. Thank you very much, and have a great day.